This is FluidKV, seamlessly bridging the gap between indexing performance and memory footprint on ultra-fast storage. It was published in VLDB this year. So we all know of persistent memory. It combines the features of DRAM and SSD at the same time and offers wide addressability and low latency. Also, key value stores, they are a pillar of modern data processing, and they're used to index a series of persistent key value pairs. They are popular because they support simple semantics for access, making them a hot research topic now. So a core component of key value stores is the index, and depending on how it operates will significantly affect the performance and the resource usage of the system. So in this paper, they divided it into two categories, single stage and multi-stage. For single stage indexes, similar to this figure, they tend to maintain a key value grain structure to route the requests to KV locations typically stored in a persistent device. So commonly, the volatile structure here is either a range index or a hash index. Legacy systems are optimized for ultra-fast storage, but to prevent the indexing from becoming a bottleneck, they usually keep the whole structure in the DRAM. So for example, for KVAL, they adopt a large B+ tree here and the page cache in memory for fast reads, and then they put all of their key value data in the persistent memory. Moving to multi-stage, I would say LSM tree is the most classical representation. In this figure, we can see that a typical implementation of LSM tree, a small DRAM storage hybrid stage 0. So first we're going to write a well, and then we're going to keep everything in a mem table, typically a skim list. And then it's going to, here it's going to persist the user writes with sequential IO. And then the other stages are sorted indexes with the help of a small coarse grain persistent index. And then we have background threads that periodically merge these stages into each other and update these persistent indexes on the side. So to demonstrate the impact of single stage indexes, which is the first one, on the performance in general, they test the write performance of a flat store and with different levels of parallelism. They perform 200 million writes, followed by 200 million reads on 8-byte keys and 8-byte values. So in this graph, we can see that mass tree, which is the volatile structure of flat store, with DRAM only B+ tree, it achieves higher than 20 MOPS in the read and write throughput, showing a very high performance and parallelism. So they extract an observation from this is that single stage indexing benefits from the high concurrency and scalability for both reads and writes in the DRAM. But of course, the key values tend to have large data values. So even if the persistent space is sufficient, the index can expand to consume large DRAM space. And especially for small size keys and values, the index may end up becoming larger than the amount of data itself because there's a lot of levels and a lot of inner nodes. And looking at this lower graph, I now understand how they did it in Bonsai KV. They set the key value to such a small size to the point that the metadata became bigger than the size of the data set itself. So this leads to another observation, which is that DRAM consumption for single-stage indexing increases linearly with the data set size at a steeper slope, actually, than the data size itself. So making the impact dominant on the data capacity. So some solutions include storing part of the index in the persistent memory to reduce the DRAM consumption, but that causes a few issues. Number one, the IO contention between the key value accesses and the index updates. Also, the small accesses to the persistent memory in form of index probes are very inefficient and they cause read amplifications, making them very inefficient for this specific structure. So in this upper graph again, we can see flat store with fast and fair B+ tree, which is a persistent B+ tree on PMEM. They call it FF tree. So it underperforms mass tree by 40 to 70% for writes and by 40% for reads. In this lower graph, we can confirm that FF tree reduces the memory footprint, but it's still proportional to the data size. It just doesn't have a larger slope. So to summarize, the performance of single-stage indexes is dominated by the index itself, and it requires careful DRAM footprint balancing to accommodate increasing data volumes and scalability.
Why is it keep increasing? The flat tree, the yellow.
This one,
Yeah.
it's
That's a flat tree, right?
it's a,
FFT?
yeah, it's FF3, but it's flat store with the fast and fair, means like the leaf nodes are part of the index in the persistent memory and part of the index is in the DRAM. So it will offload part of the data to the persistent memory, but still the part that is in the DRAM will keep increasing.
So disaggregate the storage for index and storage for data. Different.
Yes.
Medium.
Yeah.
Okay. That's the size of the index.
This is the size of the index. Yeah.
Or only index? Is that?
Yeah, this is the size of the index in the DRAM. The DRAM consumption of the index. For multi-stage indexes, they are mostly DRAM friendly, and to confirm that, they measure the memory footprint of RocksDB at different data volumes. And we can see that the consumption is consistent to 1 GB primarily because the mem table size is 1 GB. So leading to an observation that multi-stage indexing can decouple the memory footprint from the data volume. So these multi-stage indexes have a key drawback, which is I/O amplification. Each key value is written by the user, may have to be read and written multiple times because of multi-staging. And a read query may need to go through multiple stages to retrieve a target. So
that's why you get poor performance for random gap.
Exactly. So yeah, compared to
ListDB is the system published the YSDI tool.
So I'm going to talk about ListDB. The difference between ListDB and RocksDB is that ListDB will make the persistent SS tables into a scheme list. And then instead of compacting by copying the data, they will just adjust the pointers.
So that's the point by using cheaper compaction.
Yeah, but that's not good. It's not good because it causes a lot of small writes to persistent memory.
Exactly.
So
you will explain
the
disadvantage of the cheaper connection in using ListDB later.
Right now.
Okay, right now.
So many works like ListDB propose how to alleviate the I/O amplification for LSM trees, and like we said, they will merge through adjusting pointers. But pointer chasing and small random writes in persistent memory are a deadly combo. So here they test the performance of RocksDB and ListDB on persistent memory. The results in the lower graphs lead to an observation, which is that read and write performance of multi-stage indexes is limited, because earlier we are reaching up to 20 MOPS, but now it's only 4, even for
the cheaper connection technique using the PMEM that supports byte addressability.
Yeah.
Then it doesn't cause huge amplification.
Oh, the problem is PMEM.
That's their main target, right? PMEM.
It is PMEM, but the problem with PMEM is, on paper it is byte addressable, but the device itself handles blocks of 256 bytes, and then the
256 bytes
256 is the minimum internally, and then the buffer of the device buffer is cache line granularity. So even though you say, okay, the buffer is cache line granularity, I'm going to access a cache line, but I end up reading 256 from the internal device.
So if you change then just a few, like a pointer, 16 or 8 bytes.
Yeah, it will read.
26.
Yeah, exactly. So another reason here is there's tension between reads and write amplification. So for example, by increasing the number of stages, we reduce the write amplification because we can utilize the tiering when we're compacting, doesn't propagate further, but it increases the read amplification, because if we have more stages, then we may have to probe more stages to find the key that we're looking for. So another one is the I/O bandwidth usage. So they load 200 million key value pairs, which is equivalent to 3 GB of of data to all of the systems mentioned here. The baseline here uses less than 1 gigabyte per second read and 0.2 gigabyte per second write bandwidth with a single thread. And then for 32 threads, the utilization only goes up to 30% here and to 70% here. So those were FF3 and ListDB using more bandwidth because they persist index in persistent memory, so they issue more requests. The other DRAM-only indexes have poor parallelism, resulting in the underutilization. It's known that the persistent memory bandwidth is very low, but here the underutilization, here the issue is not because of the maximum bandwidth, but because of it's underutilized. So here for indexes, the persistent memory bandwidth is not really the bottleneck like we thought, but it's the structure and the access manner itself to the device. So that's what they're trying to fix. So in summary, the performance pitfalls and differences between single stage and multi-stage indexing key values lie in the architectural features themselves. So single stage indexes achieve good concurrency for reads and writes, and then the cost is significant DRAM consumption. And then in contrast, the multi-stage controls the DRAM footprint, but it suffers from low overall performance and unbalanced read-writes. So another thing is both indexes underutilize the persistent memory bandwidth due to not sending enough requests, and not because of the limited bandwidth of the media itself. So the main idea is to combine these techniques for both architectures to obtain mutual advantage. So they're going to create this single multi-stage hybrid architecture. And
You know that do they actually claim they find that trade-off?
Somehow, I would say this line might go a little bit back, but yeah. So for read, they do serve very good reads. And then for DRAM efficiency, they say if you want better read performance, you need to consume more DRAM. So the trade-off is going to be between those two now.
So it's not completely resolved.
Somehow, we're going to see later. But I would say the read does not deliver very promising results compared to what they are promising. It's like it's not very close.
That's the wrong conjecture. Wrong.
Yeah, it is.
Read, update, memory.
Yep.
You cannot get all three.
You cannot. In this case, they get acceptable improvement in all of them, but
Acceptable improvement by using the hybrid scheme.
by using the hybrid scheme and exploiting the hardware parallelism. So the goal or the claim is that this index structure will absorb the writes fast, reduce the DRAM footprint, and transition seamlessly between the stages. And here the reads are acceptable, not excellent. So this is going to be relevant later in the evaluation. So leading to FluidKV, a dynamically balanced and parallelized key value store. This is how they describe it. It's designed as a 3-stage architecture that includes a small and high performance front end, a large and memory efficient backend, and a buffer store bridging the front end and the backend stages to provide fluidity in FluidKV. So starting with a fast store, it adopts a KV grained concurrent volatile range index and the multiple thread exclusive logs. It's responsible for the fast processing of high concurrent user writes, and it allows to dynamically trade more memory for throughput under write-intensive workloads. So we can see this as a mem table, but it's not a scheme list. It's a mass tree here on top, and then here is a per thread log replacing the shared WAL.
That looks like they borrowed the mem table, mem something, mem table architecture from key value store.
They did.
Used the memory footprint.
Yeah, and they borrowed the per thread log from previous.
What other things they borrowed?
So buffer store here in the middle is an adjustable stage. They say that it enables a seamless flow between the two layers, and it converts the key value grain indexes of fast store into small sorted block grain indexes. And they will merge these sorted block indexes into stable store later. So pretty much they're flushing this fast store into a buffer tree. And then once they reach a threshold of buffer trees, it's going to be merged here.
Once they merge, they never going to fetch it and compact again.
So this one is full. It will become this. So they change the structure a little bit and they put it here. And then once we have, let's say, 4 buffer trees, which is their default in the paper, these 4 buffer trees will gonna be sort of merged here. It's like a compaction, but one time. So I have a little.
Very similar to universal compaction in the MyRocks.
Oh my.
RocksDB. Universal
It is.
compaction is just to compact all the levels at once,
Yeah,
right?
Yeah.
But they only apply just group of different levels.
so they only have 3 levels. They have the mem
Yeah.
table, and then the buffer store, which is another level of SS tables, and then the stable store, which holds all the rest in one level. So stable store here, it stores and indexes the sorted key value pairs using a set of data blocks and their index nodes on persistent memory. So they say that the structure of index nodes and the data block are IO efficient for persistent memory. It just means it's cache line aligned. That's what IO efficient in this
So
paper.
they modeled, mem table structure from the value store
Yeah.
and, apply, batching technique to different group of, level, right? Across the multiple level, multiple staging.
Yeah, we can see this as a mem table and this as an intermediary stage,
Yeah,
and
intermediary
this is
string,
the final stage.
final stage.
Yeah, and the final stage is a little bit special because usually we have like multiple stages indexed by small index or like a Bloom filter, or each SS table have its own index. But here they're going to index the indexes in the DRAM.
Index is DRAM. The main reason for maintaining the index is to expedite lookup.
Yes. So it's going to be an index of the data block.
그렇잖아. 이게 multiple level 쭉 있는데 원래는 그 리드를 lookup을 you have to perform a series of lookup for each.
I mean, here too, when we perform the lookup here, they're gonna try to find it here. If it's not here, they try to find it here. And if it's not here, then they'll find it here.
That's exactly what right?
LSM tree, right? Yeah.
They only apply batching.
They only apply batching and they put this additional range index in the whole time because all the red triangles are full in DRAM. So usually in RocksDB, they will read this from DRAM and then all of this is read or like looked up from the persistent device. So the difference is that they will kind of like reference them in the DRAM.
Okay, the first is fast store and buffer store.
Yeah.
How can you look up? How can you perform the point lookup?
I have this.
They still use the hash that Bloom filter.
They didn't mention any Bloom filter. There's no Bloom filter. What they will do is they will perform a B+3 probe here to see to see if it's here, and then they'll go through these, let's say 4 or 1 or however they have, how many they have, and they will
then maintain the mixed structure.
Yeah, so they will look up in the DRAM here and in the DRAM here and then in the DRAM here. But here, this is a range, so it's gonna lead us to a range, and then they're gonna look up another index in the persistent memory.
Recursive index.
Recursive indexing, yeah.
The main claim is, okay, here we only maintain the small size, primary main index.
Exactly.
If you cannot find in a target, then you have to fetch the second level index again, and then you should look up
Exactly.
from there.
Yeah. So this table store is gonna hold most of the key value data, sorry, and it has a very small read optimized index in the DRAM to guarantee acceptable query latency. So more details here, starting with fast store. We said earlier that shared logs can cause synchronization overhead. So fast store is going to store the incoming key value stores into multiple thread exclusive logs on persistent memory and maintain a volatile index in the DRAM. In a mem table fashion, they're going to keep the key and data in the DRAM also for faster access. And the log at this stage is just for crash recovery. And then in addition to the key value length and data, the log record also includes a 1-bit valid flag to indicate whether the key value, the value is deleted, and then a 31-bit LSN to record the written order of records for crash recovery. For persistent memory consistency and cache locality, all the records are designed to be easily aligned to 64 bytes and to save the persistent memory space when there's a log record smaller than 32 bytes, multiple consecutive small records are packed into one cache line. So why do they keep the key and the value in the mem table if they're already persistent in the log? It's because they want to keep the, many hybrid persistent memory and DRAM indexes store the leaf nodes in the persistent memory to keep the persistency without logging, but the performance is still low because of the small random persistent memory accesses induced by the index probe to the persistent memory to read the leaf nodes. So they leave the responsibility of persistent to the log, and then they just use the DRAM only range index to serve the IO, to serve IO friendly and fast reads. So like this, the index will not be the performance bottleneck and will not be a concurrency bottleneck either. The index uses fine-grained locks and optimistic concurrency control to avoid the performance degradation due to thread contention. And they need to perform a range scan on the whole index when flushing and compacting. That's why they use mastery, which is a scan-friendly structure. For the thread-exclusive blocking mechanism, logging, it improves the concurrency of log writes, which is the root cause of poor parallelism in LSM trees, which is the contention among the threads and the shared log ending. So they removed that issue for now. So buffer store here is between fast store and stable store. It's responsible for seamlessly the fast migration of the key value data from the memory intensive fast store into a memory efficient stable store. And it enables FluidKV to achieve the advantage of high concurrent writes here and then stable read latency here. And at the same time, since this is a specific, size that we're going to set to it, we will have relatively low memory footprint. So in buffer store, the key value data are indexed by multiple buffer trees that are structurally identical to this one. And I'm going to show the structure a little bit later. So when a fast store reaches its capacity, which is determined by either memory constraint or it's configured by the user, it's going to, the volatile index will be converted into a buffer tree to quickly release the memory resources by the flush operation. And similar to LSM tree, they will have two fast store, which is when this one is migrating here, they're going to populate a new one. In the DRAM.
So while the data is in the faster store is migrated into the buffer store, they still accepting all the write operations.
Yeah, so two mem tables, one of them becomes immutable and is being flushed, and the other one,
actually copy in two different storage. Right? One is currently being migrated, the other one is accepting newly inserted data, right?
So then one or more buffer trees are going to be sorted and merged to the stable store when the number of buffer trees reaches a certain threshold. And they're merged with the stable store through the compaction operation, which is a time-consuming process, of course. So the flush and compaction operations are performed concurrently, and they do not block the front end. So by keeping two mem tables. And the structure of the buffer tree is the same as the stable store, just smaller.
Keeping multiple copy is the best way to disperse, the contention.
Yeah.
They mentioned that?
They do not.
We sacrifice, space overhead to achieve, higher concurrency. That's a typical claim.
They do not.
They didn't.
No, they say we are memory efficient compared to DRAM only indexes.
That's the key message they focus on. Okay.
So the structure is designed to, this is stable store, which is the same structure as buffer store, just larger. It's designed to achieve a competitive read performance compared to just putting everything in the in the persistent device. So it's a PMEM DRAM hybrid structure consisting of a volatile B+3 and a persistent sorted blocks to index a larger portion of KVs in FluidKV. So the volatile B+3 indexes for persistent objects that are called logical sorted tables or LSTs. And each LST is an index block and multiple data blocks that it indexes. So it also holds the key and the value of an index entry in the index block and the minimum key of its index data blocks. So how are we going to rebuild this one? Each data block is going to hold the minimum of its own index block or index entry and the minimum of the index block itself. So later they can rebuild this one. The maximum number of key values stored in each LSD is the product of the number of entries in an index block, which is 4K, and the number of entries in a data block. So in their case, they use 8 plus 8 bytes. So each data block is going to hold 32 key value pairs. And the size of this index, since it's a range index, is going to be very small. It's going to be maybe 1/1024. That of the, that of a fast store compared to the other B-tree.
Size for our device, the given device you guys use.
We can decide the size. We can issue the requests at the different size, right?
Yeah, that's very the same objective that they are using. So basically, for access unit at 200.
I mean, internally. But we can issue cache line size rights from the user space.
The reason why I asked the question is we better allocate and fetch the same unit size.
Yes.
Yeah.
So we are making the order request become like make it into 256 alignment.
So they call the structure PMEM friendly, but what by PMEM friendly, they mean it's 256 to 512 bytes aligned to avoid the read modify writes from between the device buffer and the device itself, even though the persistent memory is byte addressable. So going back to buffer store, it adopts a different data migration strategy at runtime by adapting to the workload dynamics. Under the read-intensive workloads, the FluidKV will trigger flush and compaction more aggressively to reduce the number of indexes and alleviating the read amplification. So any buffer tree in buffer store will be opportunistically merged into stable store via the compaction. So under read-only workloads, FluidKV even ignores this threshold on the fastest store capacity and will trigger flush and merge immediately. So if it's a read-intensive workload, but we still have some writes, we will keep this part, but every time this part migrates to the buffer store, it will be merged immediately. So that will, because it's a read-intensive, then we can read the hot writes from here, but we can serve the reads with less amplification, so there's less probes that we do. And then if it's a read-only and no writes, they sample that they decided based on like workload sampling. And if it's read-only, every write that is entering occasionally will be merged to the bigger index immediately. And then if it's a write intensive, then they will have a bigger threshold here to stall the merge to stall the compaction process. or to give ourselves more time to absorb the writes.
So it looks like they didn't actually escape the trade-off between the memory size and the read speed.
In my opinion, it's not satisfying the claim, but they did improve. They did deliver similar read performance to other LSM trees while serving better writes and having a smaller memory.
By serving better, right? By using multiple copies of my data.
Yeah. So they're like, we don't care about the persistent memory space. We just care about reducing how much data we're storing in the DRAM.
So then the main problem of compaction operation is while you perform the compaction operation, you have to stop the all other operation until you finish the compaction. Otherwise, if you want to avoid a problem, you have to maintain copies. Right? That incurs space.
They do, even the compaction, they will perform these LSDs, they will check the ranges. Yeah, I'm going to talk about it later, but they check which range it coincides with, and then they're going to build another LSD, and then they replace it into
until you build this done, they didn't actually remove the original one, previous one.
No.
So 2 copies.
Yeah. 3 copies, this and another.
Great.
So yeah, so under, like I said, under write-intensive workloads, they temporarily tolerate more buffer trees in the buffer store, and this improves the write performance and triggers the compaction when the number of buffer trees reaches a threshold of 4 in this paper. So they say that this is because the write amplification of compaction is determined by the capacity ratio of buffer store and stable store. So enlarging this buffer store capacity reduces the write amplification because they only perform compaction once.
So it's natural reasoning.
Yeah.
If we increase the size of buffer store, then it naturally reduces the write amplification.
Yeah. Also, they dynamically balance the reads and write performance by adjusting like the space or the size of the buffer tree and the size of this index. So at some cases, they will resort to dynamically allocating more memory because if we are doing compaction here, and then we have a very write-intensive workload that is flushing a lot of tables here, then it may trigger another compaction. And that is what they're trying to avoid. While we're performing compaction, we don't want to trigger another compaction, so we're going to allocate more space. So these are going to accommodate more write.
Oh, there is a stall point, right?
Yeah.
The stall actually occurs.
It does.
If we actually push a lot of work, updates.
They try to, yeah, I mean, if we don't allocate more resources, the stall occurs. So they try to avoid the stall by enlarging these trees' capacities to make the compaction trigger less frequently. But the problem is, if we have a bigger table here, then the next compaction is going to be even longer and even more time consuming. So some details. They choose, like I said, mass tree for all of their volatile range indexes in all of the stages. It's optimized for scan because it will help them in flush and compaction. And then it's highly concurrent. So I mentioned earlier for the flush, they will keep 2 mem tables simultaneously. And the occupied memory will be freed after the flush is done, and then a new space will be allocated. For compaction, they scan all of the buffer trees and then the stable store, and then they determine the LSTs that have an overlapped range. They merge sort them into new LSTs, and then they perform something called clean compaction, which is deleting the obsolete LSTs and replace them with the new ones. So evaluation setup. They use Intel Xeon Gold CPU, which is the same as ours, and 64 GB of DDR4 and 6 128 GB Intel Optane DC memory in app direct mode. So it means that it's used in persistent mode. For workload, they ran PyBench, slightly modified, and then they use 8 and 8 byte 8-byte key and 8-byte value. The default is that the fast store will accommodate 40 million records before it triggers a flush, and then 4 buffer trees have to be existent to trigger compaction. So the evaluation results are as followed. It's good that they compared their system with a lot of other systems, but I have a theory about this. Having used the PyBench before, MB-tree, LB-tree, DP-tree are all included in the code. And if you run PyBench, it will install them automatically. So they were not mentioned in the beginning of the paper. They're just used here to fill out the evaluation section. So another thing is that they talked a lot about RocksDB in the beginning, but it's nowhere in the evaluation. And I'm going to maybe ignore a little bit the default of PyBench and just focus on the ones that were in the beginning in the motivation, which are the blue dots and the orange triangles and the dashed blue lines for mass-tree, and then the green squares for listDB, because we've discussed them prior. So writes are in figure A. FluidKV in blue shows high performance under various data volumes, slightly lower than mass-tree, which is a DRAM-only index in small scale. But for large scale, it outperforms all of them. And they say this is because FluidKV performs quick persists and performs compactions asynchronously without blocking, but also the flush does not interfere with the foreground inserts. The single stage indexes like mass-tree, they suffer from performance degradation here as the size grows because it uses up all of the available DRAM space and it starts swapping. So that's why the performance of mass-tree will go down here. Reads in figure B, they remind us of what they said earlier, which is competitive read performance with a single stage indexing. So it's not the best, but it's acceptable. And then listDB and PackTree, they have particularly significant performance degradation at the large data volumes. And listDB performs worst due to the read amplification and the low parallelism of skim lists. DP-tree performs slightly better than FluidKV, up to 20%. This is because DP-tree tends to buffer the key values in the first few stages, and it makes use of the DRAM-only indexes rather than merging the data into a persistent large stage like FluidKV. The DRAM consumption in here, figure C, it shows that mass-tree, listDB, MB-tree, and DP-tree have a much larger memory footprint than other baselines. And here they will run out of DRAM to store the key value grained index. So the reasons for this is different. For mass-tree and DP-tree, they use a large DRAM to store the key value indexes. For MB-tree, they store the inner nodes and the metadata of leaf nodes on the DRAM, but the rest in the persistent memory. And then for listDB, this one, they use a lazy memory recycling technique. So they cannot release the memory immediately after flushing the mem table to the persistent device. So it will keep it in the memory for longer. For persistent memory consumption, it shows that all of the systems have comparative consumption, about 2 to 3 times the data size. And this is due to the logs and the persistent memory indexes and the additional metadata like key value sizes and all. So mass-tree without persisting, here the index cuts the persistent memory consumption in half compared to other KVs. And then MB-tree here consumes 30% more PMEM with larger data volumes because of their inefficient PMEM space recycling. So here they're going to compare the performance scalability with a sufficient DRAM. And the 200 million random writes and reads with different levels of parallelism. In this figure, FluidKV shows write scalability, showing that they absorb the writes rather quickly, like they promised, with a highly parallelized index and their thread exclusive logging, etc. In this figure, they show the read throughput. We can see that FluidKV performs similar to most single stage and approximately up to 4 times higher than listDB, which is multi-stage. I think they didn't put RocksDB here because they didn't surpass RocksDB's performance. So overall, FluidKV's read performance is 10% lower than DB3 and MB3, but it's 2 times to 4 times higher than their write performance. So it's better than their write performance, but it's lower than the read performance. So it's a good trade-off.
And makes the workload?
There is a mixed workload. Just a second. It's in the appendix. Mixed workloads here. There is, we have here, one CSB A with 50% writes and 50% reads. Sorry? Yeah, there's no uniform workload.
Why?
Stable store will only compact the ranges that are overlapped. So I think that's why they use skewed workload.
Exactly.
Yeah.
If you use a uniform workload to support that, you have to maintain different, fragmented index structure more often.
Yeah.
That means you have to patch all the, the fragmented index into memory.
Yeah.
That increases memory pressure.
Yeah.
Right?
Yeah.
So they intentionally avoid that.
They don't say it, but we know that they intentionally avoid it. They also promise read and write efficiency simultaneously with the multi-stage indexes and data migration. They say that the trade-offs here remain, but they shifted from the user request, means they still accept their user requests, but the stall is going to happen in the background compaction, not in the user request. So the merging...
Threshold point that triggers, stall. When the write throughput reaches some certain threshold, that then it will incurs the stall.
Oh, when the merging is slower than the writes.
Merging is slow. You mean the consumption speed of the merge is slower than
yes.
The ingestion speed.
Yeah.
Right?
Yes.
Influx.
Yeah.
Okay.
So when the merging is slower than the writes, the DRAM footprint will continuously increase because the fast store and the number of buffer trees in the buffer store, and this leads to read amplification because we cannot compact them. We have a compaction ongoing. So the size in the DRAM will increase and the number of buffer stores will pile up.
Merging stage. 2 different merging stage actually occurs in this architecture, right? The first one is the fast store to the buffer tree. The other one is buffer tree to the final stage, right? The
bottleneck is the second one.
The second one.
Yeah.
If the second one is a slowdown, then it actually creates back pressure.
Yes.
All the way up to the front.
Yeah. They decide that the size of the fast store, which is the first part, is the key to trading off the memory efficiency for write throughput. So if we want to keep absorbing these writes, we need to keep them in the memory. Because if we increase, well, in this summarizing this figure, if we increase the size of the buffer store, then the next compaction is going to be even bigger and even slower.
Suppose you were the author, okay?
Yeah.
Then how can you overcome the situation, stall situation, by using what?
I think I would go back to maybe legacy, which is if we.
I mean legacy.
Yeah, I would go back to legacy because legacy is compacting us.
Technique. What technique you can apply to the existing system?
I would increase the number of tiers to avoid, I'd say, push back the compression with the last level as much as possible.
You increase you adopt what?
Means more stages, yeah.
More stages?
Yeah.
Exactly. Then it goes back to?
It goes back to LSM-3.
LSM-3.
That's why I said go back to legacy.
LSM-3.
Yeah.
Multi-stage architecture. So they will go back to the multi-stage architecture, which is what they claim to improve, right?
Yeah.
If they face, stall problem.
Yeah. I mean, they don't technically go back. This is what they do is they will increase the size of the fast store and they'll take the next large.
The size of the fast store means you can increase your memory consumption. they actually claim they improved memory consumption. So
True.
the only last resort they can rely on is they increase number of states.
Yeah. So in the paper, they mentioned some discussion, which is they said our
baseline.
So here they say that we don't offer transactional support. So we'll try to work on that in the future. And then our evaluation is fair because the baseline also does not support transactional support.
That's what they actually put in the discussion section?
Yes.
That's a big limitation.
And then they said in the beginning, they said our work is optimized for ultra-fast storage like persistent memory and CXL. And then in the discussion, they say, actually, CXL is on PCIe bus and it's a longer IO path. So we don't know how it's going to perform in that case.
Then just go back to the last evaluation figures.
Okay.
Last graphs. So in this evaluation, the key parameters are two: the size of faster storage and buffer storage. But when I read the three graphs, for me, three look almost the same.
I think it's saying that if we use a buffer store, we can increase the throughput of the compaction. Because here, this is the throughput of the compaction. So if we don't have a buffer store, it means we are flushing the data directly from a fast store to the other to stable store, which is maybe a smaller, how to say, operation. So it doesn't utilize, how to say it. When we increase the size of a buffer store, it means we are compacting more data. So it makes sense that we are using more throughput. I don't think it means that the buffer store is the main contribution specifically.
No problem. Then what's the key contribution?
The key difference, I would say, of their system from other systems is that usually we're going to here have only the mem table serving fast reads, and then the rest of them will serve significantly slower reads compared to the DRAM only indexes. But in their system, they will put a small index in the DRAM to route all of these persistent memory indexes. So to expedite the read of what we could even use on a traditional LSM tree. So if we come here in the legacy and then we bring all of these indexes to the DRAM, then I would say it may also perform similarly.
Much rather.
Okay, thank you.